From Diamond Light Source, this is the Diamond Podcast.
This is the Diamond Light Source Podcast with me, Mira Senthilingam. In this first edition for 2010, we probe into the synchrotron itself to find out what makes diamond such a useful tool in scientific research, as well as discover how its X-ray beams are created with such accuracy and intensity. We'll be investigating how the design of a synchrotron-like diamond is crucial when the research it's used for operates at the micron level.
We derived a specification of the flow being stable to 1 micron over 10 metres per hour and 10 microns over 10 metres per day. If a human hair is 40 microns diameter, you could imagine that over a day we're not wanting the flow to change by more than a quarter of a human hair.
We also find out how the movement of such high-speed electrons is controlled.
They monitor all the parameters, they can see summary screens, they also have alarms if something goes wrong. Most of those are updated 10 times a second, so people see the information in real time.
Plus, we discover how electrons moving at this high speed are manipulated to create the right light.
If you control how far the electron beam moves from left to right, then you actually control the color of X-rays that come out from that process.
All that, plus the latest news and events from Diamond, coming up on this month's Diamond Light Source podcast.
The Diamond Podcast. For more information, look us up online at diamond.ac.uk/podcast.
Previous editions of the Diamond Podcast have provided an insight into the fields of research taking place at Diamond. But this month, we're looking at the workings of the machine. This research that takes place works on scales as small as microns and nanometers. That's 1/1,000,000th of a metre and smaller. So we're going to investigate how such precision and stability are enabled at this level. So first, we meet Jim Kay, Head of Engineering at Diamond Light Source. He explained to me how producing accurate beams of light on this minuscule scale requires careful design and planning from the outset.
In designing and building diamond, one of the key things is the stability of the electron beam. The electron beam is the source of the X-ray photons that are then transmitted to the beam lines for science. So if we have an unstable electron beam, then we'll have unstable X-rays. Also, where the X-rays are used, down where they are exposed to a sample, if the sample similarly is wobbling around and isn't stable, then the data produced from the X-rays falling on the sample won't be very good either. And in designing diamond, in order to achieve that stability, we paid a lot of attention to minimising the sources of vibration. Hence, all our main plant, like water pumps, compressors, heating and ventilation fans, are all housed well away from the accelerators and the beam lines.
A key thing you were looking at was maintaining a constant ground level, essentially, in the area of the synchrotron where the actual beam lines would be, and keep that separate to, say, walkways and other pieces of land that essentially would move more, I guess, and be used more by machinery and people.
Yes, one of the key features of the diamond slab, where the accelerators and beam lines are that we've built this slab on piles. This slab is about 650 metres in circumference and about 30 metres wide. It's a continuous ring, and the ring is built onto 1,500 piles, dug 12 to 15 metres deep into the chalk that we've built diamond on. And one of the key things with this site is that the water table varies each year. In the wettest months, the water is only about 4 metres under our feet. In the driest months, it's about 12 metres under our feet. And with that varying water table annually, the chalk shrinks and swells, and we couldn't afford that kind of behaviour being replicated on the surface of the slab where our experiments are. So by drilling these piles into the chalk, we've achieved a very flat, reliable and stable platform.
And what other features are there that just further ensure that the actual ground level here doesn't change as, say, the chalk beneath us swells and shrinks?
Another design feature we've built into diamond is that underneath this slab there's a 70mm gap. which allows the chalk, as it shrinks and swells, to do so into the void and not affecting the level of the slab.
How much can a change of the ground level essentially change the beamline by? And how much of an effect would that then have on the samples that you're trying to look at?
In our specification, we were conscious that a typical beamline experiment might last a shift, a day of 7 or 8 hours. So we're keen to achieve a great deal of stability in that one shift period. So hence we derived a specification of the floor being stable to 1 micron over 10 metres per hour and 10 microns over 10 metres per day. And to get those numbers in perspective, if a human hair is 40 microns diameter, you can imagine that over a day we're not wanting the floor to change by more than a quarter of a human hair.
So now you've distinguished between the slabs used in the main experimental hall part of the synchrotron and then the actual walkway that's surrounding it. So we're currently standing in the experimental hall, and I can see a very long rod of metal is what it looks like to me, which is a special piece of machinery you use here in order to ensure and check that your ground is as accurately maintained as you hope.
Yeah, this system is called a hydrostatic levelling system. It's a canal, a water canal, that's 60 metres long. It goes from the source of the X-rays inside the storage ring tunnel and stretches out along a typical beamline route, 60 metres to the edge of the experimental hall. And what this canal allows us to do, at various points we've fitted sensors, and you can see one here. It's typically about 125 millimetres diameter steel pot, about 200 millimetres tall, and inside there is the open surface of the water canal and a capacitive sensor that's built into the top that's checking the height between the top of the pot, the HLS sensor, and the level of the water canal inside it. And so we've got 8 of these sensors, 10 metres apart, and if we measure the height change between adjacent sensors, and we can check, are we actually achieving that performance with this instrument?
So essentially this is a very large and very accurate spirit level.
That's exactly right.
And now, a way you're taking this a step further and just ensuring greater levels of accuracy to greater distances is with your new I-13 beamline. So what's happening there?
Yes, I-13 is one of our later Phase 2 beamlines, our so-called coherence and imaging beamline. We want to build an experimental station that's 250 metres away from the source of the X-rays.
That's very far.
It's a long way, and a typical beamline that you can see here, the experimental sample will be of the order of 40 metres away from the source of the X-rays. So we're looking to take the X-rays more than 6 times further away from the accelerator than we've done to date.
What are the benefits of having a beamline 250 metres away?
We're getting dimensions in perspective. A micron is a millionth of a metre, or a thousandth of a millimetre. A nanometre is a thousandth of a micron. And the next era of scientific beamlines will aim to achieve nano-focus beams, whereas at the moment, with these shorter beamlines, we deliver micron-focus beams. You can focus to smaller sizes the further away you are from the source point.
Is progress going well, and when's it going to be ready?
Progress is going very well. We've cast the slab, we're building the building now. That's due to finish in the spring, and expecting our first photons delivered to that end station by the end of this year.
That was Diamond's head of engineering, Jim Kay, explaining how keeping the ground on which Diamond was built stable is crucial to ensure the accuracy of the beamlines created. Now, Diamond was completed and began operation in January 2007. So now, 3 years on, I spoke to Diamond's technical director, Richard Walker, to find out the highlights and achievements that have taken place in this time, and what we have to look forward to.
Well, the main achievements over the last 3 years have been not only a significant increase in the number of operating hours, more than 50% increase in 2009 compared with 2007, But we've also doubled the beam current, we've doubled our reliability of the machine, and we've doubled the number of insertion devices in the ring. We've also introduced a top-up operation.
What's top-up operation?
Top-up operation is a means of operating the storage ring. Instead of injecting the ring with beam twice a day, it's now injected every 10 minutes, so it maintains a much higher average beam current.
And how does injecting, say, a beam then every 10 minutes, how does that increase the stability?
Injecting the storage ring every 10 minutes means that we maintain more or less a constant beam current, and that means there's a constant thermal load on the storage ring and on the beam lines themselves, so it maintains a much greater level of stability.
And so how many beam lines have actually come into operation and been used by users since Diamond began in 2007?
Well, since 2007, when we started with 7 operating beam lines, there's a further 10 come into operation since then.
So that's quite a few. Have any of these been particularly challenging in terms of creating them or getting them into operation?
Well, all of the new beam lines are challenging in one degree or another, but one might mention particularly the infrared beam lines and the bending magnet beam lines in general. There's been some issues there that we've had to tackle. In particular, for the infrared beam line, B22, we've had to make a significant modification to the storage ring. We had to modify one of the vacuum vessels in the storage ring in order to allow the very highly divergent infrared radiation to come out from the storage ring and use it in the beam line. And that has involved replacing a vacuum vessel, which we did by building up a separate girder unit and then swapping the girder units, which is quite a major operation. In November 2008, I think we did that.
Now, what about upcoming challenges? So what's planned for the year ahead?
Well, in 2010, again, we'll increase the number of operating hours compared with previous years. So, of course, this means there are fewer shutdowns. So there's still quite a lot of work to be done installing new insertion devices, new front ends, but they have to fit into a much tighter programme.
OK, so that's essentially 17 beam lines that have come into operation by now. And how many more are hoped then for the year ahead?
Yes, we have 17 operating beam lines now, but Phase 2 is well underway, and that will bring us to a total of 22 beam lines, and that will conclude in 2012. So we have 5 more beam lines to come into operation in the next couple of years.
That was Diamond's Technical Director, Richard Walker.
Did you know that Diamond has vibration detectors so sensitive that they picked up 10 earthquakes in 2009, including the earthquake in Tonga, 10,000 miles away?
You're listening to the Diamond Light Source podcast with me, Meera Senthilingam. This month, we're probing the workings of the synchrotron itself. And coming up, we'll be finding out how magnets are used to manipulate electrons as they circulate around the synchrotron to create the right forms of light, as well as reveal how such high-speed electrons, combined with thousands of magnets, are actually controlled. But before that, let's join Sarah Bucknell from Diamond's communications team for a roundup of the latest news and events that took place at Diamond towards the end of 2009, including the first users on the new infrared beamline.
That's right. It's our first infrared beamline, B22, and we've had some scientists from Keele University and the University Hospital of North Staffordshire, and they're using B22 to study lung cancer cells.
And how are they using infrared to look at lung cancer cells?
Well, they're looking for the characteristic markers of cancer, essentially to work towards an easier and quicker way to classify tumour development in patients in the future. So the ultimate aim is to find and set up a method that could be used in hospitals, which applies infrared light to basically detect early signs of cancer as an aid to diagnosis. They're hoping to eventually be able to pick out cancer cells from healthy cells, and basically before the cancer cells grow and form a tumour.
Now, as well as this beamline having had its first users, a new beamline has just had first light.
Yeah, that's B18, our core XF beamline. They had first light towards the end of last year. This beamline uses X-ray absorption spectroscopy.
And what can be done with X-ray absorption spectroscopy?
Well, it's an established technique that provides element-specific information about the atomic geometry and the chemical state of the absorbing atom in your sample. So it can be used on solids, liquids and gases for basically any field of science. And B18 is one of our 3 spectroscopy beamlines, so it's going to provide a complementary facility which will basically allow for more general, less demanding experiments.
So rather than focusing in on very specific things, it'll provide users with a more general insight and overview on certain areas.
That's right. It will be ideal for just one-time access or for new users in spectroscopy.
OK, now, as well as all of this, Diamond also got a new instrument that's going to make particular existing beamlines even better.
That's right. This is a new instrument that will be used in the Surface and Interfaces Research Village. It's the Reflectivity and Advanced Scattering from Ordered Regimes End Station, but we call it RASER for short. And basically, it's a soft X-ray diffractometer that enables scientists to study electron systems by probing their magnetic charge and orbital structures.
How does this actually work to enhance the activity of these beamlines?
Well, it's an end station which has been built specifically for the beamline for the Advanced Dichroism experiments. That's BLADE I-10, which is currently under construction. But whilst that's being completed, it will be situated on IO6, which is our nanoscience beamline, and it will be used for diffraction and reflectivity experiments.
And so what kinds of areas of research can benefit from this?
So RASER will be useful in fundamental research. It would form a good basis for the pursuit of a new generation of electronic data storage equipment, for example, ultra-fast memory devices.
And, well, Sarah, it is the beginning of a new year, 2010. So what's coming up at Diamond to look forward to this year?
Well, we're going to have some exciting features on local radio and TV as part of BBC's Year of Science. We're also going to be featuring in the Royal Society Summer Science Exhibition in July later this year. It's an extended 10-day exhibition to celebrate their 350th anniversary. And as well as that, we'll be in Turin in Italy at the Euroscience Open Forum, delivering a symposium on the latest from synchrotron science in Europe and North America.
And what about back at the fort? When can people come and have a look at the next Inside Diamond Day?
So the next public Inside Diamond Day is Saturday, 27th of March, and those who are interested to come along can look on our website for more details.
And the website address to find out more about Inside Diamond Days is diamond.ac.uk. That was Sarah Bucknell from Diamond's communications team, who'll be back in the next edition with more news and events. Now this month, we're investigating the workings of the Diamond synchrotron. So now, we meet Mark Heron, head of the Control Systems Group, to find out how electrons moving round a storage ring are controlled.
In the control room, we operate the 3 accelerators that make up Diamond Light Source. These are the linear accelerator, booster synchrotron and storage ring. In this process, we first produce and accelerate the electrons in the LINAC. They're further accelerated through the booster, and we accumulate the electrons in the storage ring. It's the circulating electrons that then produce the synchrotron radiation that are used by the beamlines and experimental stations.
Now, you mentioned that this is all controlled from the control room, but how is this actually managed from a remote source then?
This is controlled in the control room by an operation team consisting of 2 people. They control the 3 accelerators through a distributed control system. This enables them from the control room to be able to operate any of the thousands of pieces of equipment that control the technical systems that make up Diamond. So if we look at the technical systems, there are thousands of power supplies, hundreds of pieces of diagnostics, hundreds of interlocks that form a machine protection system, a safety system, radiation diagnostics, and all of these are controlled through the distributed control system.
Now, that sounds like a lot of things to control at one time, and you mentioned that 2 people do this. So how is this possible? How many things are just visible at one time or working at one time in order to monitor so many things at once?
This is possible because we bring the information from all these technical systems back to operator displays. We present the information in detailed and in summary form. And through the summary form, it's possible for operators to see the state of thousands of devices on a simple overview page.
So now we're just by your computer now, and you've got a couple of possible screens that can be seen from the control room. So what have we got here, and what's this kind of telling us about the state of the synchrotron at the moment?
Okay, so the first screen shows us the state of the 1,200 magnets that make up the LINAC booster and storage ring. And all of these magnets are electromagnets and are energized through DC power supplies. What we're looking to see is that power supplies for these magnets are on, they're set at the correct level, so that the magnet is then at the correct field. And from this summary page, we can see the state of magnets grouped by family and by location. And if all the magnets in a given family and location are working correctly, then that's shown as green. If the page is all green, life is good and the magnets are ready to run.
Now, an interesting screen you've got also is a graph, basically showing you whether the beam is going through the centre of the storage ring.
It's very important to be able to control the position of the stored electron beam, because that determines the position of the photon beam that travels down the beamline to the experimental stations. We control the position of the electron beam by measuring it in 168 locations, and we measure it vertically, whether it's high or low, or horizontally, whether it's to the left or right of a central orbit. And this is done by electron beam position monitors. And when the machine is working correctly, this shows the beam in the centre of the vessel, which gives you a reading of 0x and 0y.
So say that the beam is slightly higher and it's at, say, 5 on the x-axis. What would you then be able to do in order to get that back down to 0?
If we had a 5mm error on the x-axis, a machine protection system would have dumped the stored beam, because that would have resulted in damage to the vessel that contains the beam. To prevent that happening, we run a feedback system that automatically corrects magnets to bring the electron beam back down to its central orbit if it starts to drift away.
So I guess an important thing then is that from the control room you're able to see things like where the magnets are, where the beam is, the power supplies, but more importantly you're also able to make changes to then correct any problem.
Very much so. Diamond is quite a large facility. The storage ring is over 0.5 kilometre in circumference, and it's just not practical for people to have to walk to a technical system to switch it on or off or change a value. Diamond is operated as a facility 24 hours a day by the operators. During that time, they monitor all the parameters, they can see summary screens, they also have alarms if something goes wrong. In terms of the parameters that are on the screen, most of those are updated 10 times a second, so people see the information in real time.
Now, it's obviously impossible to be able to control absolutely everything, though, so could something go wrong with the synchrotron, and if so, what can be done about it?
A number of things can go wrong when we're operating a synchrotron. There are thousands of technical systems, and in the case of many of those, if they fail, that fault will be so serious that the electron beam will be lost. If we think that electron beam goes around 500,000 times a second and the electron beam can be lost in a few turns, then it's lost very quickly. The other possibility is that a technical system can go wrong and the electron beam stays in an orbit where it's going to produce a photon beam that will damage the vessel. In those cases, the machine protection system has to recognise this invalid operating condition and protect the vessel by actually dumping the stored electron beam.
Mark Heron, head of the Control Systems Group at Diamond. That's almost it for this month's podcast, but before we go, we look into the use of magnets at Diamond to control the path of electrons as they flow around the synchrotron storage ring. Emily Longy is an insertion devices physicist, and she works with insertion devices to create bright, forward-flowing beams of light. I met her inside Diamond's storage ring to find out more about the workings of the machine.
Right now we're on the experimental hall floor where we keep our spare girders. These are the girders that hold all of the magnets that comprise the storage ring. So this is basically 1/24th of what's inside of the tunnel. On these girders we've got quadrupole magnets, dipole magnets, and sextupole magnets. And the dipoles are basically like mirrors that bend the electrons around a corner. And the rest of the magnets are like lenses that focus them into a very small spot in between the girders where we use them to actually make the X-rays.
So just next to the girder here now, there's a big gap, which I assume then soon an insertion device will go.
Right. So if this was actually installed in the storage ring, then we would have a continuous vacuum pipe between this set of girders and the next sector. And in there, we would either put magnets inside of the vacuum, which then produce the X-rays, or we have a vacuum vessel that we close magnets around.
So there's a lot of magnets being used here, essentially, to get the different types of beams or different types of light that you want.
That's right. Synchrotrons are basically magnetic devices from one perspective. You're using magnetic fields to change the behavior of a charged particle.
So you mentioned now, after going through these girders, you would put insertion devices that would then control this beam further. What is an insertion device?
So for us, an insertion device is either something called a wiggler or something called an undulator. And basically what it is it's a series of magnets that change the direction of the electron beam, normally sideways. So it'll go left, then right, then left again. And it'll do that many times over a couple of meters, say. And if you control how far the electron beam moves from left to right, then you actually control the color of X-rays that come out from that process. And that's the only thing that the users are interested in, really, controlling the color of X-rays that they get in their beamline.
Okay, so we're now about to head out to an area where a wiggler type of insertion device is being made at the moment.
That's right.
So, Emily, you've now brought us to a particular type of insertion device that's being built at the moment. So what are we looking at here?
We're looking at a hybrid wiggler at the moment. So what we've got here is two beams separated by about an arm's length at the moment vertically, and we can close them down next to each other. And the top and the bottom both have arrays of magnets and pole material. So the magnets are made out of something called neodymium iron boron, which is one of the strongest rare earth magnets in the world. And then in between them we have a special kind of iron that changes the direction of magnetic fields very effectively.
So this 2-metre-long magnet, which is a wiggler, will be placed in the path of an electron beam to do what exactly then?
So the electrons will actually pass in between the two arrays of magnets, and as it passes through, it'll experience a vertical field. And if you have a charged particle moving through a magnetic field, then you get a force that's perpendicular to both the main direction of movement and to the field. So we've got vertical fields here, and that means that we get a force horizontally. So as the electrons pass through here, they're actually going to wiggle back and forth from left to right.
What's the benefit of that happening?
The whole point of a third-generation light source is to have insertion devices which provide tunable X-rays. So we can control the color of X-rays that come out. And the way that we control the color primarily here is by allowing the user to change the gap between the magnets. That changes how far the electrons move from left to right, and that changes the color of X-rays that are emitted.
Now, you say colours of X-rays, so what does that mean exactly? How does that actually differ in its properties?
Just like on the radio, you can tune to different wavelengths, say 98 or 94 megahertz, or in the visible part of the electromagnetic spectrum, you've got red light, you've got green light, and you've got blue light. The X-rays are part of that continuum of electromagnetic radiation, and you can change the wavelength of the X-rays that are produced.
So this particular type we've mentioned is a wiggler, but there's also another type of insertion device known as an undulator. So how does this differ?
The easiest to explain difference between a wiggler and an undulator is that when the electrons enter into the magnetic field, they either move left and right farther than the, say, size of the electron beam, or they move left and right smaller than the size of the electron beam. So the distance that they travel is shorter than the total spatial extent of the electron beam. If you stay inside of the electron beam, it's an undulator, and if you don't stay inside of the electron beam, it's a wiggler.
This is what makes Diamond a third-generation synchrotron. What does that mean exactly? Why is it third generation?
So the first generation of synchrotrons were parasitic. They had built the synchrotron for some other purpose, and somebody figured out that they made X-rays and stuck an experiment in the way. Second generation expanded on the idea and was dedicated to the idea of using the light. The third generation really has optimized the design of the entire storage ring in order to provide the very best quality electron beam where we put the insertion devices in order to provide the brightest X-rays possible.
That was Emily Longy, insertion device physicist at Diamond. Now, that's it for this edition of the Diamond podcast, but do join us again in March, when we'll be going back to the research to bring you the latest scientific discoveries and work taking place at Diamond. In the meantime, if you have any questions about Diamond or the research taking place there, the email address is podcast@diamond.ac.uk. Or you can listen to previous editions of this programme online at diamond.ac.uk/podcast or nakedscientist.com/diamond. You can also subscribe to the Diamond podcast on iTunes. Thank you this month to Sarah Bucknell, Jim Kay, Richard Walker, Mark Heron and Emily Longy. I'm Mira Senthilingam. Thank you for listening and I'll see you next time.
The Diamond Podcast is brought to you by Diamond Light Source and produced by thenakedscientists.com. There's more information on our website at diamond.ac.uk/podcast.